you give me an example of a combustion reaction? In both of these cases, we have methane here and an acetate molecule. But where else does combustion happen?
Internally.
Internally where?
My engine.
In your engine, yes. Combustion engine. The engines of your cars. Unless you have an entirely electric vehicle, the thing that is powering them is the combustion of fuel. Taking our, in this case, gaseous fuel, but what we usually use is liquid fuel that is injected into a container that therefore allows it to form a pseudo-gaseous state, which we then burn it with a bit of oxygen, creating a whole buttload of water and molecules and lots of energy. That heat and those extra molecules take up a lot more space than the original molecules, especially, it doesn't look like it here because we have one molecule of methane and two molecules of oxygen. It goes to form one molecule of CO2 and two molecules of water, right? So it's the same amount of molecules. But when you talk about octane, the stuff in your car that you're burning in your engine, octane is called octane because it has 6 carbons in it. So it would be 6C6H, well, a couple of other things, but C6H1214, C6H14. That combined with a little bit of oxygen is going to create a whole bunch of carbon dioxide and a whole bunch of water and energy that makes those gaseous molecules occupy even larger space, which is what pushes up the piston in your engine, which is what turns the crank, which is what turns the shaft on your wheel, which is what turns your wheel, which is what makes you go. Where else is this happening? Campfires? Combustion reaction. The sugar, the carbon, organic molecules in the wood that burns, that releases a whole bunch of energy that we like to stare at. Where else is it happening? Inside every single one of your cells. This reaction, this combustion reaction, is where you're getting the energy to sit there and listen to me. Burning the sugars that you got from the foods and the drinks that you consume to get ATP to maintain your homeostasis so that you can continue existing. It's a combustion reaction.
Citric acid cycle?
Yeah. What do you start with? Sugar. What do you end with? CO2, water, and energy in the form of ATP. It is a combustion reaction that is coupled to electron transfer that allows you to capture it. It's the same reaction that happens in a campfire, it's just uncontrolled and uncaptured there. It's a mild simplification, but yes, it's a combustion reaction. A propane heater, fireplace, or a wood stove is burnt. You have to make sure that it's ventilated for 2 reasons. One, if you don't give a combustion reaction oxygen, then you are literally not giving it something that it needs to happen. And without oxygen, there is no reaction. 2, you're producing a lot of CO2 and a lot of heat. What do you call something that produces a lot of gas and a lot of heat in a contained environment? Eventually the environment will no longer be contained. And what do we call that? An explosion. Otherwise known as a bomb. Which is also quite literally what your car engine is, a controlled explosion. Lots of very tiny explosions in synchronized order to move your car forward. 2 molecules of methane plus 3 molecules of oxygen, both as gas, form 2 molecules of carbon dioxide, 4 of water and heat. Hold the phone! What did this mean again? It means we have to add energy. What? What? Heat is energy, right? So why do we have to add energy if we're getting energy out? Well, allow me to ask you a simple question. Most of you have paper in front of you in one form or another. What's the primary molecule that makes up that paper? Do you know?
Cellulose.
Cellulose, otherwise known as sugar. CCH1206. Sugar, that's the simplest formula for sugar. Sugar, which is a carbon compound. It's the same thing that your cells are burning for fuel. It's the same thing that you burn in a firewood fuel, or a very simple form, this methane here. Why is your paper not burning right now? Well, right. What would it take to make it burn? Add heat. How much heat would you get out of it? A lot more than you added, right? Which is why a match can start a forest fire. Because this heat is much bigger than that heat. And therefore, it can be used as the heat to start the next reaction of the next atom. Or maybe 2 or 3 or 4 or 12 atoms. Carbon monoxide is a result of incomplete combustion. How do we know that? How could you already know that? What do you know about, and I'll give you a hint, it would have something to do with drawing dots. What do you know about carbon monoxide that would infer to you that this is incomplete combustion, that there is still more reaction that can take place between carbon and oxygen when we deal with carbon monoxide?
The outer valences aren't happy.
The outer valences aren't happy yet. Carbon itself does not yet have a full outer shell, right? And so it still wants to react with something. The most likely candidate would be oxygen. Carbon monoxide is colorless, odorless, and it is quote-unquote poisonous. The reason that it is poisonous is because it will permanently attach to hemoglobin. Now the thing about iron in your hemoglobin, in your blood, that iron atom, it likes oxygen, oxygen likes it, but they don't form, they're just dating, really. They're not really, going steady or whatever other euphemism there is for something before marriage. They are not permanently attached. Even marriage isn't permanent. They're not permanently attached. They're just hanging out for a little while. But carbon monoxide, when it meets up with that iron, it is like a obsessive, compulsive, codependent partner that will not let go. And if it won't ever let go, then that means that molecule of hemoglobin can no longer carry oxygen. If you breathe too much of this, it means that you can suffocate as if there was no oxygen in the room, even though there might be plenty of oxygen in the room, because blood without red blood cells, without hemoglobin, cannot carry enough oxygen to keep your brain alive. And carbon monoxide permanently destroys your hemoglobin's ability to carry oxygen. Question?
So it's the chemical rickroll?
It's the what? Yes.
Chemical rickroll.
Permanent, well, metaphorical chemical rickroll. Yes. If you're not sure what that is, Google it. Rickroll. Yeah. If you don't know, it's okay. You can live without this knowledge.
No, we can always talk from
The song gets stuck in my head.
Yeah. Reduction in exercise capability, visual perception, manual dexterity. It's because your blood has a reduced ability to carry oxygen. And the only way to recover that, get new blood cells. Like your red blood cells can't make more hemoglobin. So this takes a while to recover from, and in severe cases, sometimes requires transfusions to save your life. Because the only way to fix it is to get fresh blood, which takes a while for your bones to do that. You're constantly making more blood every day. But a bad enough exposure to this that's not quite enough to kill you, that could take weeks for your body to recover normally. Hey, here's all of what we just talked about, but with some extra numbers. If we lose 10% of our hemoglobin and we just sort of feel it, headache, drowsiness. 30% severe symptoms, dizziness, mental confusion, severe headache, nausea, and possibly vomiting. At 50% or more, unconscious and die. You need a lot more oxygen than regular liquid can carry. That is why we have so many red blood cells. Each one of those red blood cells has, I don't know, I'm going to say millions, possibly billions of molecules of hemoglobin. And every single one of them is carrying a molecule of oxygen that your blood would otherwise not be able to carry. This is why we care about carbon monoxide. And that is why it is so dangerous, because of that bullet point there. Colorless, odorless. And the only thing that frequently saves people's lives is carbon monoxide is actually more dense than regular air. So where are you going to find it? Close to the floor. Unfortunately, if you're in a burning building, where do they tell you to go? Down to the floor where it's cooler.
CO2 will kill you too.
Yes, exactly. So will the hot air and everything else. So, you know, take the good with the bad. If you get out, they can hopefully give you a blood transfusion. But anywhere that you have a lot of combustion, like your house burning down, you're going to get some carbon monoxide.
270 million molecules per cell, 20 to 30 trillion red blood cells in your cell.
Nice. That's a lot. Still not 6.02 times 10 to the 23rd lot. But you get close. Million is 7, or no, 3. It's like million is 6, trillion is 12. 6 plus 12 is 18. So it's close. So, reaction types. Combination, decomposition, which are just inverted, right? Single replacement or double replacement, or combustion. So that was a somewhat undefined list at the beginning of this section. Does it make a lot more sense now? Oxidation reduction reactions. Otherwise known as redox. Oxidation reduction. Redox. R-E-D-O-X. Reduction, oxidation. Oxidation, reduction. So we need to understand what oxidation reduction reactions are and which ones are oxidized and which ones are reduced. Oxidation reduction reactions are any reaction where we are exchanging electrons. Which means it's all of these. Remember I told you what was making that hydrogen ions, the hydrogen gas appear when the zinc was dissolving? Because there was an exchange of electrons, right? Redox reactions, oxidation reduction reactions, these are the things that we get our energy from our food. These are the things that allow for electrical energy in batteries. This is what occurs when iron rusts. This is what makes the Statue of Liberty green instead of bright, shiny, penny copper. Oxidation reduction reactions. How could we, okay, so we get energy from food by capturing the energy released in oxidation reduction reactions. But how could a battery work? How can that work? What is an oxidation reduction reaction? It's an exchange where one atom is giving up electrons and the other atom is gaining electrons. If we take those two reactants and put them on opposite sides of an electrode that allows electrons to move, then this guy can take electrons from the electrode, which draws electrons from the donor at the beginning, and suddenly we have a battery. And so how does a battery go dead? The guys who were donating electrons run out. And the guys who are accepting electrons are full up. When that happens, your battery is dead. It's the exact same chemical reactions, we're just separating them in distance and taking advantage of the current of electrons that that separation creates. That's all a battery is. So, oxidation is loss. Oil rig. Oxidation is loss. Reduction is gain. So when we're talking about oxidation reduction reactions, you can use the oil rig, not acronym, what's the word for this? Oil rig. Word with letters that means something else. It's also somehow supposed to help you remember something.
Acrostic.
Hmm?
Acrostic.
No, I don't think that's what I'm looking for, although it might still apply. An acronym? An acronym. Yeah, I think it's an acronym. Which is different than anachronistic, which is probably why I was confused. I think it's an acronym. So, oil rig, oxidation is lost. Here's another way to look at this. Think of this like a score, okay? So, A and B. A is giving up an electron. So let's say that both A and B start with a score of 0, i.e. they are both elements straight off the periodic table, okay? What is happening to the score of B when it gains an electron? What's the score for an electron? -1, right? So the score for B is doing what? It's going from 0 to -1. And by any measure, what would we call that score? It is being reduced, right? Reduction is gain of electrons. The atom that is being reduced is the one that is gaining electrons. Therefore, the atom that is being oxidized is the one that is losing electrons. A is oxidized via the loss of electrons in the act of reducing B, which gives us, by definition, what? If we started with a score of 0 for both A and B, what do we now have? A is now a what?
Ion.
Ion, and so is B. So what happened to A's score? It went from 0 to +1. Because however many electrons it had before, to make it balance, it now has one less. So now it has more protons than electrons, right? So it's now +1. Oxidation and reduction. The Statue of Liberty, that outer layer, if not the entire thing, because I'm not sure about the entire thing, is copper, pure copper. When she was made, when she was first made, she was bright, shiny, new penny, golden brown. I guarantee you she was not bright, shiny, new penny, golden brown by the time she got to America. Because they shipped her over the ocean. And salt water is horrible for rust. And that's pretty much what that outer patina is. It's rusted copper. Question?
Okay, so back to oxidation reduction.
Okay.
So because A becomes positive, does that mean that B would become negative because it gained electrons?
If they both started at 0, yes.
Okay, so B is negative. So it would be
Yeah.
-1.
Yeah, B is -1, A is +1. On the product side.
Okay.
On the reactant side, they're both at 0. Now, I'm put a little asterisk next to that because that is true under the assumption that we're starting at 0. If A started at -2, then it's still going to be negative. It's just going to be -1 because it gave up 1 electron, right? So, and B could have started at +4, and now it's +3. But like, the score is going down for the reduction because it is gaining electrons. Oxidation is loss, and reduction is gain of electrons. It's the electrons that are moving. The electrons are the hot potato. That's the thing that's moving. Protons don't move. If protons moved, we'd be talking about particle radiation. It's not what we're talking about.
So you're saying this is only for product, not necessarily for the oxygen? Okay. I'm sorry.
No, I'm saying that the electron's moving, so A will still be A.
Right,
A does not turn into C,
okay.
because the electrons are the things that are moving. If protons moved, A would become C, nitrogen would become carbon, right? So protons are not moving. And if the protons aren't moving, then the only guy that's left to move is electrons. Oxidation reduction is the movement of electrons. It's the gain or loss of electrons. In fact, all covalent reactions is the gain or loss of electrons, the sharing of electrons. Because protons can't really move from the nucleus. But electrons are way out there. And they can hop around. They can be a little bit more promiscuous. They can jump from one atom to another. Yep.
I like that way to describe it.
So, 2 copper as a solid becomes 2 copper plus 2. The process of becoming plus 2, because there are 2 of them, it gives up 4 electrons, right? Those 4 electrons are accepted by oxygen to form 2 negative 2 ions of oxygen, and then those 2 ions combine to form copper oxide. Normally copper and oxygen, solid copper, does not give 2 rips about regular gaseous oxygen. They don't care about each other. But under the right conditions, if they swap electrons, then you will create 2 ions that very much do care about each other. They will form a solid oxide. And that's what makes the Statue of Liberty green.
Except for the torch, which is covered with gold.
Sure. That's what makes the copper surface of the Statue of Liberty green. It's because of the oxidation of the copper. Which is also, as I believe I pointed out very earlier in this semester, why Vulcans have green blood. Here is a solution of zinc sulfate. Here, or copper sulfate, excuse me, solution of copper sulfate. Here's a zinc strip. When we put that zinc into that solution, what is happening is that zinc is becoming plated with copper. So here's what's happening down here. That copper ion in solution, right? It's copper plus 2. So it is interacting with the surface of zinc. And at that surface, 2 electrons are being transferred to the copper, creating a zinc ion. A zinc ion does not get along as a solid, so it leaves and floats out into the water. But that copper is no longer an ion, and things that aren't ions don't stay in water. So it's got to stick to something. Conveniently enough, there's a solid metal right there that just had a hole made in it. So I'll just hang out right there. So we are exchanging a zinc atom for a copper atom, which is why when you pull this bit of zinc out of that copper sulfate solution, what you end up with is a zinc bar with an outer layer of copper.
Does it require electricity?
In this case, no. There are other ways of plating, yes, like gold-plated things, yes. Why would, okay, it's a good question. He asked, does this require electricity? Why would that be a good question to ask here? What is electricity?
Electrons.
It's the movement of electrons. What is happening here? Are electrons moving?
Mm-hmm.
Yes. In this case, it's the movement of electrons that is entirely spontaneous because this is an exothermic reaction. You could do this exact same thing with something that does not want to swap electrons. And that's how you end up with gold-plated things and silver-plated things. By forcing the movement of electrons via the addition of energy in the form of electricity. Electroplating surfaces, causing the deposition of metal ions. Well, deposition of metals that are no longer ions. So, how does oxidation reduction happen in biological systems? there's a molecule called FAD, flavin adenine dinucleotide. It can be reduced to FADH2 by the transfer of 2 hydrogen atoms and 2 electrons. Now, your body, where do the hydrogen ions come from? Well, this is happening inside your cells, which are naturally just slightly acidic. And we haven't talked about it yet, but what does an acid do? What is an acid? It's a concentration in aqueous solution where we have a concentration of hydrogen ions, just literally just protons, free floating protons with no electrons. But anything that is even marginally acidic is going to have a lot of free floating hydrogen ions. So, we have 2 hydrogen in biological molecule. Those hydrogens and the electrons that are coming from that reduced molecule is going, or excuse me, the oxidized molecule is going to reduce this coenzyme FAD, and so the hydrogen atoms are going to come right along with it. The electrons that we're drawing by oxidizing a biological molecule, we are capturing those electrons, and therefore capturing the energy that they carry. And the way that we keep that FAD molecule balanced is by bringing on a couple of protons with it. 2 hydrogen protons and 2 electrons. The body metabolizes methyl alcohol, an otherwise poisonous substance, via all of the following reactions. So we start with methyl alcohol. We oxidize it in one step, so it loses 2 hydrogens and it becomes formaldehyde. Is this equation balanced? How many carbons do we have on the left? 1. How many do you have on the right? 1. How many oxygens do we have on the left? How many do we have on the right? Same amount. How many hydrogens do we have on the left? 3 plus 1 makes 4. How many do we have on the right? 2 plus 2 make 4. So it's balanced, right? So we're taking this methyl alcohol, we oxidize it to formaldehyde. That formaldehyde then further reacts with oxygen to form formic acid, which is yet another oxidation step. We then further oxidize that formic acid with more oxygen to form CO2 and H2O.
There's a MASH episode that dealt with a very real situation that was happening in Korea, whereby people, South Koreans would take normal alcohol bottles and use a diamond bit to drill a hole in the bottle, remove the real alcohol, replace it with the much less expensive wood alcohol, methyl alcohol, and then poison the troops.
Nice.
And make a tiny profit.
This is also why they say if you drink moonshine, you'll go blind. Because moonshine, if it's not properly done, could also have a relatively high concentration of alcohol.
Oh, from the antifreeze in there.
From the production process.
Mhm.
Yes.
You just gotta clean it good.
Oxidation is always going to involve the loss of electrons. It is sometimes seen as the addition of oxygen, which is why we call it oxidation. Now, if we are adding oxygen because that is who is receiving the electrons. So we're taking electrons from the molecule, oxidizing gaseous oxygen so that we actually have oxygen ions. And then those oxygen ions are combining with the molecule. But it's still oxidation. We're still removing electrons from the original molecule, giving them to oxygen, and then the oxygen is immediately reacting with the molecule. Because here's the thing, normal oxygen doesn't like to react. But you give it a couple of electrons, and suddenly it really likes to react. How many of you guys have heard of something called free radicals? Or reactive oxygen species. These are the things that you need antioxidants for. You should have a lot of antioxidants in your diet, right? This food's good for you because it's antioxidant rich. Why is that? Because redox reactions that occur in your body create oxygen radicals. They create oxygen that really does like to react with things. And that's necessary. Your body is doing that on purpose. But the problem is sometimes it loses control of a few of them. And they can make messes. And the thing about antioxidants in your food is those chemicals are really good at cleaning up those messes, at soaking up all those oxygen ions that are highly reactive. Because normal oxygen is not an ion. It is not highly reactive. But you hand it a couple of electrons and suddenly it's like a preschooler on a sugar high. It's going to make a mess. If you don't give it something to play with, it'll find something to play with. And you may not like the outcome. Reduction always involves the gain of electrons. It might be seen as the loss of oxygen. How would that work? Well, if you take two oxygens that are only there because they were turned into ions, if you rip away the electrons that were keeping it interested in that toy and make it balanced again as a molecule of O2, it doesn't care about playing anymore. And so it leaves. So reduction is sometimes the loss of oxygen. It could also be seen as the gain of hydrogen. Because if you add electrons to something that increases the negative charge, right? Well, how could you easily balance out a negative charge? Especially in an aqueous solution? Add a few protons, right? Add a few positive charges. What's the easiest way to get a positive charge? Hydrogen ion. And in a slightly acidic solution that is your entire body, there's a lot of hydrogen ions to spare. All right, anybody have any questions about oxidation reduction, at least in terms of what we've talked about? We're not getting into too deep into the different things you can do with that, but oxidation reduction is the vast majority of all biochemistry. Loss or gain of electrons, and then the reaction of the molecules that result from that loss or gain of electrons. As far as test questions go, what's losing electrons? That's the thing being oxidized. What's gaining electrons? That's the thing that's being reduced. How can you tell if it's losing or gaining electrons? Well, this slide's a nice crib sheet for that. Oxidation reduction is one of those things that I have seen previously students have a hard time understanding conceptually. I'm not really certain why. But I just know that it's a hard, like, it's an easy thing, I guess, to get flipped around, turned around in your head. Oxidation is loss of electrons. Reduction is gain of electrons. Because that's the only thing that can move. Electrons. Right? Protons can't move. Neutrons can't move. Not unless we go back to chapter 5 and start talking about radiation. And that's not what we're talking about here. I don't like making things like protons can't move. Like, well, technically, like, that's chapter 5, we don't care about that. We should, but we don't have time. So, all right, let's talk about mole relationships and chemical equations. So we talked about what a mole was, right? How we can see molar relationships, how to balance an equation, right? Then we talked about the type of equations that you could see, that you might be looking at. And now we're back to understanding how the relationships of moles works inside that reaction. So here we have iron plus sulfur goes to form iron 3 sulfide. Would you say that the physical properties of these three pictures are very different? They're all solids. Yes, but they take their different shape, they have different color, they have different density, they have different chemical properties. because we are going through a chemical change to form iron 3 sulfide. I do think it's somewhat cheating to show this iron 3 sulfide as the actual ore, as opposed to taking the iron 3 sulfide and grinding it up. But, you know, that just kind of helps to illustrate the chemical change that is going on here. Law of conservation of mass. We have discussed this before, we just didn't call it the law of conservation of mass. We did say specifically that we cannot create atoms and we cannot destroy atoms, right? So we've been talking about this the whole time. The mass of the products, therefore, is equal to the mass of the reactants. If we have a balanced chemical equation, balanced mole to mole from products to reactants to products, then that means that the mass would be the same. A mole of carbon on the left side of the arrow weighs exactly the same as a mole of carbon on the right side of the arrow. Two moles of silver plus 1 mole of sulfur goes to form 1 mole of silver sulfide. 215.8 grams there, 32.1 grams there, and what do those two things add it up to? 247.9. Conveniently enough, exactly the same weight on this scale on the right. Conversion of matter. We cannot create or destroy atoms. So these two numbers here add up to exactly that number there.
Are there ever any exceptions to that?
We can say no in air quotes if you want, because the only exceptions to this would be if we were combining 2 moles of this and 1 mole of this to make, say, 1 mole of this and 1 mole of hydrogen gas, which obviously would not be weighed here, right? But by weight, yes, it is always the same. Whether or not everything you make is going to be weighable on a scale is a totally different matter. But yes, by weight, 2 moles of silver, 2 moles of silver. Because the only way to change the weight would be to somehow change the number of protons or neutrons, right? Because that's where 99.9997 of the mass of an atom comes from. And since we're saying we can't do that, then it would have to be the same, right? Reactants, products. This is Avogadro's number in parentheses. That's exactly the same thing as saying 2 moles of silver. That's 2 times 6.02 times 10 to the 23 atoms of silver, right? That's just including the conversion in the category, right? Reading equations in moles. We've been doing this the whole time, right? There's a reason why I've been saying it that way the whole time. This equation, 2 iron as a solid plus 3 sulfur as a solid goes to form iron sulfide. 2 moles of iron plus 3 moles of sulfur makes 1 mole of sulfur sulfide. But what do we know about this? The weight of these 5 moles of material will exactly equal the weight of this 1 mole of material, right? Because we cannot destroy or create. But it only works that way if we have a balanced equation. If we got rid of these numbers, iron plus sulfur goes to form iron sulfide, that would not work anymore. Because that would infer that 1 mole of iron and 1 mole of sulfide somehow makes 2 moles of iron atoms, right? And 3 moles of sulfur atoms. That wouldn't make any sense. So we have to balance it first. And once that is done, then we can do all sorts of math with it. If I told you the weight of iron that I gave you, and then also told you the weight of iron sulfide that it made, could you tell me the number of moles of sulfur that you had in that reaction?
Yes.
Just algebra, right? There are 3 variables here. If I give you 2 of them, you can solve for the 3rd, right? Because math is math, and we're trying to keep it simple and obvious, what this whole slide here is for is to show you that when we're doing some math, we can make mole-to-mole ratios for any 2 substances. So, what is the molar ratio of iron to iron sulfide? 2 to 1. 2 to that number that we never write because it's just inferred. 1. Right? What's the molar ratio of iron to sulfur in iron sulfide? There are 2 ways to see that. You could say it's 2 to 3, or you could say it's 2 to 3. And that's exactly what we have right here, 2 to 3. And just like any other ratio, you could write it as 2 iron over 3 sulfur, or 3 sulfur over 2 iron. When are these conversions going to be useful? If I'm asking you math about how many moles of iron there is in how many moles of iron sulfide, right? You can either do it in your head, or if you need to write it out so that you can make sure that you're right, these are the conversion factors that you're going to use. How many moles of iron oxide can form from 6 moles of oxygen? So this is the ratio of iron and oxygen to make iron oxide. So what's the relationship between iron oxide and oxygen? There are 2 moles of iron oxide for every 3 moles of oxygen that you use to make it, right? 3 moles of oxygen for every 2 moles of iron oxide. So even though this slide seems to be totally screwed up, see if that looks any better like this. Nope, it really doesn't. Oh! Why don't you do this?
Slide 70.
Thank you.
You have to type it in.
Can I type it in? 7, nope, get that. I can grab this and drag that, that's probably fine. 70! Dun, 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 and hit click the button. Okay, so, 6 moles of oxygen times 2 moles of iron oxide per 3 moles of oxygen, right? That's why they're giving us these factors right here written out like this. It's to make this type of math easy, to make sure that you're doing this right. So, 6 times 2 divided by 3. Why not 6 times 3 divided by 2? That's still a ratio, right? We could have 3 moles of oxygen to 2 moles of iron oxide, right? But would that give us... Right, it wouldn't cancel out the O2. We'd have moles of O2 squared over moles of iron oxide, and that would mean nothing to us, right? So we draw it out like this so that we can make sure that we're crossing out what we started with, moles of O2. And we end up with an answer that makes sense for what we were asked. How many moles of iron oxide? Does our answer have moles iron oxide as the units? Yes! Then we probably did it right.
Why is it 4.0 instead of just 4?
6.0 moles.
Yeah.
Oh, yeah.
Okay.
Because this right here is an exact ratio. Right? So it doesn't affect sig figs. Realistically though, what they should have had right here is 6.0 moles. That would have made it a lot more obvious. Because yes, otherwise you're like, I don't know, that's a good quote. It's because they told us 6.0 right here. It's a good question though. It means you're paying attention to those sig figs. It's good. ghost that's just... The one thing if I was touching the smartboard, that's why I'm not using the smartboard. Anyway, all right, let's talk about mass calculations. We've already talked about this whole section we've already talked about. But now we're just going to talk about mass calculations in terms of whole equations, instead of mass calculations in terms of moles of an atom. But it's the same thing, right? We just have to balance the equation first. So, given a balanced chemical equation, we can calculate how much of a substance B we get from a known amount of substance A. If we then convert moles of substance A, or moles of substance A to moles of substance B, we can get a molar ratio, and then that can be used to turn it into grams. Why do we have to have a molar ratio? Because a mole of an atom is that much, right? The atomic mass of an atom is its weight in moles, but you have to have it in moles first, right? But remember, anytime you have a chemical equation, that is telling you the number of moles, or at least the ratio. But the question might be something weird like, if you start with 4.2 moles of something, how much of this other thing would you get? Well, you have to know the molar ratio of the products and reactants to do that, right? Like this right here, 32 grams of nitrogen. What is the mass of ammonia that we can produce from 32 grams of nitrogen? How do we do that? Well, first we have to know how to convert nitrogen into ammonia, right? So that's N2. Why not just N? Well, yes, but nitrogen never comes as just N. Just like hydrogen, oxygen, fluorine, chlorine, bromine, and iodine. There's that table back in 6, don't remember which chapter, where it's like these are the diatomic ones that always come in twos. That's why it's N2. N2 as a gas is not just N. So it has to be N2. Plus H2, right? Because hydrogen also comes as a diatomic atom as a gas, diatomic molecule, right? So conveniently enough, NH3, this makes this easy, right? So NH3 here, we have to have 2 nitrogen here because we start with 2 nitrogen on the left, put a 2 there, that means we have 6 hydrogen, so how many H2 molecules do we need? 6 divided by 2, because each H2 molecule brings 2 with it, so 3. 3 times 2 is 6, 2 times 3 is 6, right? So are we balanced now? Yes! Great! Now what do we do? Well, we have 32 grams of nitrogen. Okay, so what's the first step? We know that this is the balanced equation, so that means that we know the molar rate. What is the molar ratio of nitrogen to ammonia? Tell me what it is. 1 mole of nitrogen per 2 moles of ammonia? Is that right? What do we think? What's the problem with that? Is this 1 mole of nitrogen? It's 2 moles of nitrogen. There's a 1 there, but what do we have to do? 1 times 2. It's 2 moles of nitrogen atoms, right? So 2 moles of nitrogen is equivalent to 2 moles of ammonia, right? 2 times N. So that means it's actually a ratio of 1 to 1, right? 2 to 2 is the same as 1 to 1. So, 32 grams of nitrogen. How many moles of nitrogen is that? How do we calculate that? 32 grams of nitrogen. How many moles is that? Well, to get that, we would need grams per mole of nitrogen, right? Or more specifically, moles per gram of nitrogen. Where could we find that? Where would we look that up? Where's a table that gives us all of that information? Right over there. Nitrogen is 14.0067, which if we're rounding to 4 significant figures is what?
14.01.
14.01 grams per mole, or 1 over 14.01 moles per gram, right? So if it's 14 moles per gram, how many moles do we have here, ballparking? 2 point something, right? 32 divided by 14.00, or excuse me, 01 is 2 point something. So if we have 2 point something moles of nitrogen to start with, how many moles of ammonium are we going to have? Well, it's a 1-to-1 ratio, so what's the answer? 2 point, right? Let's see if we're right. Are we real confident that we're right? No? No confidence at all. Come on, guys, you can do this. So here's how it's doing this. It's going grams of nitrogen to the molar mass of nitrogen to the mole-to-mole factor of nitrogen to ammonia times the molar mass of ammonia in grams. That's a whole bunch of blah, 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 right? Let's follow along. What? I did not say any more. I never said there wouldn't be any more math. Never said that. I said that by adding chapter 6, there would be considerably fewer math questions in exam 1.
Oh, you tricked us.
That did not mean you were done with math.
Exam 1 was great, so if you could just leave it like that, I would.
Yeah. I kept
I was
waiting for the math.
Me too. He tricked us. I was like, no.
Oh, there's one. This is going to start the avalanche.
No.
And then there's one more.
Yeah.
Not every question will be a math question.
2 of my questions on the exam were the exact same.
Really?
About the exact same question or the exact same
It
wording?
was about gold. It was like, what is the source
Yes.
of gold? And then just asked me again, I'm like,
Yeah.
Wait.
That's the beautiful thing about randomness.
I
But
didn't
because
even
there's
know questions.
a thing. A equals 2B, and then later on if it's like, does 2B equal A? Like 2 different ways of asking the same thing.
yeah.
Like, if you got lucky that you happen to get that, but that's one of the ways that you inflate the number of questions. That you can ask the same question 3, 4, 5, 6 different ways. And if you understand what you're talking about, you've got all 6 of those down. If you're just guessing, then you're going to go A, D, C, B. I don't know. So, if you didn't have any clue, then you might have gotten one or both of those wrong. But the reason you got them is because RNG, right? Like, yeah, go love RNG. Anyway, so let's see. What did we actually do? Do 39 grams of nitrogen. We said it was like 14-ish, 17.03 grams of ammonia. Right? We just didn't finish it out all the way to the end. What were we asking for at the beginning? How many grams of ammonia? So we did everything right, we just didn't finish it. We said that there was 14 plus, right? Ballparking it? Which is what that 17 was. And then what's the last step that we needed to do? If that tells us how many moles of ammonia, what do we got to do? Multiply that by the molar weight of ammonia to find out how many grams we have. Grams per mole. 1 mole of nitrogen is 28 of N2 is 28.02, or I mean they're calculated by gaseous nitrogen, so they're multiplying N times 2, 14.01. Here's 1 mole of ammonia. That's the molecular weight of 1 nitrogen and 3 hydrogens. Here's 1 mole of nitrogen equals 2 moles. 1 mole of N2 equals 2 moles of NH3. That's still balanced, right? Because it's the ratio of 1 mole of N2, which is the same thing as 2 moles of nitrogen. Is this math making sense? We're getting confused? Hopefully it's making sense, right?
I thought it was a 1 and 1.
It is. if you're comparing N to NH3. They're comparing N2. Which is why it's half, 1/2. So 1 to 2, because we've doubled that top one, 1 mole of N2. When we did our math for a 1-to-1, we assumed that we were already going to cut that N2 in half. So it was just 1 atom of nitrogen.
So we skipped a step.
Yeah, we put 2 steps together is what we did. Because that difference is going to come out the same at the end. They still came up with, we came up with 14 plus some, right? Which is 1703. I'm sure we would have gotten that one if we actually plugged it into a calculator. And that's the amount of ammonia that we have, but then to figure out, or in 1 mole for there, you plug that in, and you get 39 total grams of ammonia.
How'd you get 2 to 1 again?
This here?
Yeah.
This is 2 to 1 because it's 1 of nitrogen gas to that. But see, what they did was they put 2 to 1 here, but then they had the weight of N2. We had a 1 to 1, but it was 1 mole of nitrogen is 14 grams of nitrogen. So this was half as big, and so was that. You see?
No.
Right? 2 times this. So, look at this bottom one here. Right? So all we did was we just moved that 2 to there to make it 2 to 2 or 1 to 1. See it now? Because they're doing moles of N2. We did mole of N, which makes it 1 to 14.01, which means that we don't need this anymore because ours is 1 to 1, so this whole thing goes away. So we combine 2 steps. But otherwise the math is the same. Everybody follow? We're actually ahead of the game. Oh my gosh.
Yes.
Is it cold in here?
Always, always.
I just set it up. Okay.
This building is always
Well, it doesn't help that it's trying to stay cold, and as the night progresses, the outside gets cooler, so we're not losing as much ambient heat, and so therefore the same amount of effort produces greater difference. Actually, let's talk about energy and chemical reactions, Joe. So for 7-9, we want to be able to tell the difference between exothermic and endothermic reactions. Alright, in order for this to happen, we have to understand a conceptual limitation of reactions. So here, I'm going to put this in terms of metaphors. Remember, actually, I'm going to give you a specific example and then put it in terms of metaphors. Remember we were talking about dissolving the zinc in the hydrogen chloride? Where was the hydrogen bubbles forming?
On the surface.
On the surface of the zinc, right? And not above the water, and certainly not like away from the zinc, just kind of in the liquid, right? At the surface. That is because all chemical reactions require contact. By way of metaphor, what does it take for me to shake your hand? Contact. Which requires us to be close enough that when I reach out with my hand and you reach out with yours, they can grab each other in a relative shaking position with possibly, but not required, the motion of actual shaking.
Yet never touch.
Technically, yes.
You said it.
I know. I did. Yet never touch beyond the repulsion of the electron density of the surface of your hands. But, let's take that metaphor a little bit further. If a chemical reaction is the metaphor of us shaking hands, of me reaching out and shaking your hand, there are a lot of ways for that to go wrong. First off, we have to be close enough to touch. If I'm all the way back here and I'm trying to shake anybody's hand, that is not going to work. It doesn't matter who you are in this room. That's not working because I'm too far away from you, right? But even if I did get close enough to shake your hand, I could stick my hand out in any number of ways and impact you in any number of places that were not your hand or appropriate or either. Right?
Or both.
Right. That's the or either, or both, like together. I could reach out and poke you in the nose. I could reach out and pimp slap you upside the head. Pull an NCIS or something, right? Like, there's a lot of things I could do. Many of them would be inappropriate. But the only way that would result in us shaking hands is if I reached out and took your hand, and then we, like, sort of shook a little bit, right? Forward. Yeah, no fun. What does that mean? So that's the metaphor. So hopefully that inappropriateness sticks. I found that inappropriateness helps things stick. Collision. That is the act of touching, right? In the case of shaking hands, the actual hand-to-hand. But it also takes orientation. If you are facing towards me, the likelihood that I will successfully shake your hand increases exponentially. If you are facing any other way than towards me, the likelihood that I will shake your hand is virtually zero, right? I mean, I could like try really hard to do a reach around type thing, but that's still just going to be really awkward. What? I did not take it there, you took it there. You're the only one laughing. Remember, I'm being recorded.
And put on.
Yeah, exactly. To live forever. Anyway, so collision, orientation, and the thing that doesn't sort of work for this metaphor is energy of activation. I guess by this metaphor, it could be one of those things where I could be next to you and in front of you, but if I just don't care about shaking your hand, then it still isn't going to happen, right? Like if I'm not motivated, if I'm not really trying, it's still not going to happen, right? Chemical reactions require all three of these things: collision, orientation, and energy of activation. That hydrogen appearing on the surface of the zinc in hydrochloric acid, that's collision, where the zinc is touching the water, where the hydrogen ions can touch the zinc in order to swap electrons. But what if that aqueous solution was frozen? Do you think that reaction would happen? No. What is that? That's a kind of reaching for, if an extreme example, of the energy of activation as a limitation. Even if we're close enough to touch, if I don't have enough energy to be motivated to try, it's not going to happen. This right here, the energy of activation, that is why the paper in front of you is not bursting into flame right now. Because here's the thing. True or false? The paper in front of you is undergoing a combustion reaction right now. True. It's just happening really, really slowly.
Like a Windows explanation.
Sort of. Maybe.
Remember, like old houses you talked
Yes,
about?
yes.
1800s.
Like glass being old glass being a liquid. It's just really, really slow. Yes. Because see, here's the thing. And we haven't gotten to it yet, but combustion reactions are exothermic. That means they give off energy, which means they are spontaneous. You don't have to add energy to make them work, except even some of those reactions you do. You have to add enough energy to make it start. But here's proof. In a completely impossible hypothetical scenario. Let's say that we could take a microwave and through a little bit of modification, turn it into a microwave time machine. Not that can go back in time, but just make time speed up inside of it. So let's take a piece of perfectly good paper, put it inside the microwave, set it for 100 years, wait 30 seconds for it to finish, and then open the time microwave machine. What's that paper going to look like? Is it going to be pristine and beautiful? No, it's going to be yellow and brittle. What's happened to that paper? Time, yes, but in enough...
Microwave won't affect it. There's no water.
Right, there's no microwaves in this microwave time machine. It's not actually being heated, it's just being elevated through time. So the point is that over those hundreds of years, that paper is burning. Some of the molecules, every now and again, happen to run into or collide with an oxygen atom with just enough energy, due to random chance, that it will react, because it is an exothermic reaction. But the rate is so slow that it may as well be zero. But what could we do to speed that rate up? Add energy. Add enough energy to raise the average energy of all of those molecules, and what would happen to that page? It would burst into flame. What happens to a bit of wood if you put it on your stove? Eventually it will catch fire, even though there is no open flame there. Put it up, yeah. Take a piece, well, you can do this without wood. Take a piece of paper towel, put it on top of your stove, and little bit of stove, right? Make the stove nice and hot like you're boiling some water. When you pull it off the water, take just the edge of your paper towel, lay it down on top of that nice little red bit. Nobody's going to be amazed that it'll burst into flame. But it doesn't take open flame to make fire. It just takes enough heat to motivate the atoms to react. And once that starts, that kicks off a chain reaction. If enough of them start at the same time, then a chain reaction will happen, and your paper towel will burst into flame.
So you won't put stuff on a hot surface.
Or why, if you accidentally leave something on a hot surface that you didn't realize was still hot for a little bit too long, you take your glove and you go, oh crap, and you pull it off, and you've got charred bottom of cooking glove, which might be a personal anecdotal story, maybe. And a trip to Walmart to find out how much cooking gloves cost. Why? Here's the thing. In an exothermic reaction, the products have less energy than the reactants. Remember earlier on in our discussion about reactants and products, well, not even reactants and products, but just atoms, the reason that they react is because they want to achieve the lowest energy state possible. Entropy is telling them, you have too much energy, cool your jets. If you can find a way to achieve a lower energy state, you will go there. But here's the thing. The act of getting into those bonds, of forming those bonds, took energy in the first place. They are relatively relaxed, even at that higher energy state. To force them up, think about it like a valley. Literally like a valley. If I draw this a slightly different way, if we take, say, two things and react them to form a complex of AB, if the end product here is higher in energy than the beginning, then we have to pay for that. We have to add enough energy to force them to take that shape. That's what plants are doing with CO2. Where do they get the energy to make sugar? Sunlight. They're taking energy and forcing atoms to take a shape, to form bonds that have a higher energy level. Now, when we combust them, we are releasing them back down into A plus B, back down into carbon dioxide and water. and we're getting the energy out of them. But what do we have to do to start that process? We have to get them out of this hump. Imagine that this is literally a hill and you are pushing a ball. What is it going to take to get a ball from here to here? You've got to push it uphill, right? But once you hit right here, what's going to happen? It's going to take over and roll down the hill by itself. But if it's resting down at the bottom of this valley, how are we going to get it out the other side? What do we got to do? We have to add a little bit of energy again, but what's going to happen as soon as we're up here? Gravity will take over and it'll roll the rest of the way down, releasing a lot more energy than we put in. If the products have less energy than their reactants, then it is an exothermic reaction, which means that if conditions are right, i.e. if the activation energy is low enough, it will happen on its own. That is why paper slowly burns. If we take carbon and hydrogen, it takes 18 kilocalories to turn it into methane. But when we burn it back into carbon dioxide and water, we will get some of that energy back out. I say some, because the energy it takes to get over that hump right there, we're not getting all of that back. We are not going to capture all of this energy. We're going to capture as much of it as we can. But you remember that law of conservation of mass? There is another fundamental law of thermodynamics that says no reaction is ever going to be 100% efficient. Every time a plant takes CO2 and makes sugar out of it, it is losing some of the energy. Every time we take the sugar and burn it back into CO2 and water, we lose some of that energy as heat, as unrecoverable heat. Do you have a spider back there?
It's like a weird looking bug, I don't know what it is.
Okay.
So it's gonna die.
Don't I think I cut off the head? Oh, I'm sorry.
So that's an exothermic reaction. If an exothermic reaction is one where the products have less energy than the reactants, what's an endothermic? An endothermic is where the products have more energy. And entropy does not like that. And so we have to pay for that difference. And not just the difference for the heat of the reaction, we have to pay to get all the way to the top of that hill. But we do get some of that energy stored in the fact that that new molecule has a higher amount of energy than it started with. Here, heat is a product. We're getting heat energy out from an exothermic reaction. In an endothermic reaction, heat is a reactant. If you don't add heat, and a significant amount of it, you don't get anything. This reaction right here, nitrogen plus oxygen form nitric oxide, that does not happen by itself in nature. Now there are some natural processes that can do that. Remember when one of the first days of class we talked about how difficult it is to get fixed nitrogen in a form that biology can use? Because nitrogen, that N2 right there, remember that N2 is held together by a triple freaking bond. It takes a buttload of energy to break all three of those bonds, which is what you have to do to get free nitrogen so it can react with oxygen. That peak right there for nitrogen is huge. But the reactants are still relatively high energy. How do I know that that's relatively high energy? What could we do? How do I know? Well, here's this. How do I know that this is relatively high energy? Because what if I did this in reverse? What if I took these reactants and tried to break them down in a decomposition into those products? What would I get? That energy right there would be one of those products. I would get a lot of energy out of it. Here's the thing. How many guys have ever gardened enough to like add a little bit of fertilizer to your garden? Or mix a little bit of Miracle-Gro, a little bit of fertilizer? Maybe. Unless you're talking about either stuff from your compost or quite literally animal waste, like you can get horse manure, cow manure, and mix that in. That's good too, because it has nitrates in there. But you can also just get pure fertilizer, nitrate fertilizer. It's good for plants, used sparingly. Less is more when it comes to that type of fertilizer. But there's a reason why it's difficult. If you're going to go, like let's say you're a farmer or otherwise you want to go buy a whole bunch of this, if you buy more than a certain volume of this type of fertilizer, you get put on a federal list. You know why?
Mix it with diesel fuel, it's an explosive.
Because before we had something like that going on, a guy named Timothy McVeigh blew up the Oklahoma City building with a U-Haul full of fertilizer and a little bit of gas and a tiny little explosive. Add just enough energy to get over that hump, and what do you get? A whole lot of energy out the backside. And that's chapter 7. With a little bit of time to spare. Were it not for the fact that 8 is so short, I would pick up 8 and go. But are we good for tonight?
Yes.
Yes.
All right.
That's a lot of information.
It's seriously, there's some math in here, but not as much as you. A lot of that math is just conversions, moles to grams, right? The hard part is balancing your equations. The hard part is this right here. If you need practice, practice that.
So if we get some of those problems in this chapter 8 is shorter, we ask questions about them.
Yep. And in fact, chapter 8, we're probably going to end up spending time going through some of the practice problems anyway, specifically because of that reason. But chapter 8 is once again another really math-heavy chapter. So we might spend a lot of time going over practice problems from both chapters tomorrow, or Thursday. We'll see.
So it's just now equations chapter 8 or like?
Chapter 8 is gas law. So it's going to be lots of things. Let's put it this way. A whole lot of remember when we were talking about how a gram is equal to 1 cubic centimeter of water at sea level at room temperature?
Oh, those type of questions.
Yeah. So what happens to a volume of gas when it goes from this pressure to this pressure, or from this volume to this volume? How does that change the pressure? So gas, there's a lot of, and it's one equation, but a lot of different shifts this way or that way.
Because it's like a cost problem.
Yeah.
Oh,
It's one equation where one variable is shifting from one side to the other. So what does that do to the rest? If the temperature isn't changing and the volume is, then the pressure has to. If the temperature is changing but the volume isn't, then the pressure has to. So it's a lot of what happens when this goes up, well then this goes down. What happens when that goes up? Well then that goes up too. So it's all about that. But that's all about math. The way you show that is all math. But there's only 3 ways you can do it. So that's why it's short.
Okay.
But it's all math. So fun. Question?
I have a question about that.
Yes, ma'am.
So, question number 42.
Okay. I will preface this with, you should email me about this, but continue to ask, because that will be my record of whether or not I did.
Okay. So, like the right answer,
When, can you catch the, or whoever goes out the door next? Yeah, yeah.
That's using significant figures, but that has grams of a milk.